Okay, so picking up from where we were, hopefully you've tried these 3 questions and hopefully your answers match mine. But what I wanted to focus on is the format of your answers and the layout. And I want you to notice a couple of things about the way I've done it, because when I look at your work, whenever you're doing differentiation, I want to see the same layout. And I always have what you call, what I'd call a block of 4 in the top right, and I would do this as soon as I answer a question. And it doesn't matter whether I'm using the product rule, the quotient rule, or the chain rule. What I want to see in your work is this block of 4. So a u, a v, a du, and a dv for the product rule. For the quotient rule, a u, a v, a du, and a dv. And for the chain rule, just very slightly different. The y, the u, the dy, and the du. And the reason I want you all to do this is because right at the start it allows you to be really clear about your different elements for answering the question, to get them down and to then be able to use those for the rest of the question. It's very easy when you're doing questions like this, especially when they get a little bit more complicated, to misuse a u instead of a v, or a du instead of a u. And all my experience tells me that if you're really clear and you write those 4 things down at the start, first of all, if you do make a mistake, you're likely to get more credit than if you're just trying to bluster through. And second, you're less likely to make a mistake. So first thing is, I always want to see you use the block of 4. The second thing is we should always state the rule. So you can see here, stated that I'm using the product rule, and I've written the product rule out. You can see here, stated I'm using the quotient rule, and I've written the quotient rule out. You can see here, stated I've used the chain rule, and I've written the chain rule out. Again, this is a way of us both reducing the chance that we're going to make a mistake, and ensuring that we get as much credit as possible from an examiner, even if we do make a small slip. So I'll run through using that method for the examples a little bit later, but right now what I want you to do is to look at the next box down and the derivative of tan kx. And my understanding is you haven't seen this before, but what I'd like you to do is I'd like you to see if you can come up with the derivative yourself using one of the rules. And I want you to think about what tan is in terms of sine and cos. I want you to think about what word is going to go in here, and then I want you to have a go, either in your notes or in your workbook or on a scrap piece of paper. Can you come up with the derivative of tan kx yourself? Pause the video, give yourself a chance to have a go. Okay, I'm assuming you've had a go, and the rule that you would have tried to use is, of course, the quotient rule. Because we can use the fact that the derivative of tan kx is the same as the derivative of sine kx over cos kx. And that gives us an opportunity to use the quotient rule. And if I'm going to use the quotient rule, the first thing I'm going to do, just like I showed you, is do my block of 4. So for the chain rule, I need u, I need v, I need du by dx, and I need dv by dx. And u is the numerator, sine of kx, v is the denominator, cos of kx. Sine differentiates to cos, but I remember to bring the k in front, so k cos of kx. Cos differentiates to minus sine, but again bringing the k in front, minus sine of kx. And then using the quotient rule, so dy by dx equals v du by dx minus u dv by dx all over v squared, and substituting in this case, I have cos of kx times by k cos of kx. I have minus sine of kx multiplied by minus k sine of kx, and that is all over cos of kx squared. Doing a little bit of simplifying here, I can see I've got k cos squared, I can see I've got a minus sign and another minus sign which will make it positive, and I can see I've got a k sine squared. So this is going to be k times cos squared kx plus sine squared kx, and that's going to be all over cos of kx all squared. And cos squared plus sine squared is 1, giving me k over cos squared x. Cos squared x, or 1 over cos squared x would be sec squared x. So my answer here is k sec squared kx. That is a new rule, and one that we can add to that table at the beginning of essential derivatives that we don't need to reprove, that the derivative of tan is sec squared. So, using that new one, we have an opportunity now to put this layout into action, and what I'd like you to do is focus on the next 3 examples, but I'd like you to be really careful to use the layout exactly as I had it above, the block of 4, stating the rule, working through to your solution. Pause the video, have a go. Okay, so I'm guessing you paused the video and you tried all these questions, so let's run through them. First one, I can see I've got a function of a function. So it's an example of the chain rule. And doing my block of 4, the outside function is y equals tan of u, whereas the inside function is u equals 5x squared plus 3. I do my derivatives. dy by du this time is sec squared u, using the rule we just learned, and du by dx is 10x. So the chain rule states that dy by dx is dy by du times by du by dx, which means I just have to multiply these. Before I do that, I'm going to think about which one goes first. I'm going to put the 10x out front, and then sec squared of u. But because u is just a dummy variable, and I only introduce it to make solving this easier, what I'm then going to do is substitute back in for x. So sec squared of u is sec squared of 5x squared plus 3, and that is my solution. Okay. Part B. Again, we're going to use the chain rule here, but it's interesting in that things have switched around a little bit. And in this question, y equals tan cubed of x, which is the same as y equals 10 of x all cubed. And if I write it in that way, it helps me see a little bit more clearly what's the inside function and the outside function. So the outside function here is y equals u cubed, where u equals tan x, and then I can do my block of 4. dy by du is 3u squared, du by dx is sec squared x. So stating the rule, dy by dx is dy by du times by du by dx, and substituting in, 3u squared would be 3 tan squared x times sec squared of x, and that's our solution. Got a little bit more space on the back here for the last one. The last one had a little trick to it. So The question, of course, was if y equals sec squared of 3x, how can we differentiate that? And I guess a key thing for us to think about here is we just haven't done how to differentiate 1 over cos or sec squared. And a really good thing for us to have in mind when we're doing questions like this is we have to always take it back to something we know how to do. There probably is a way through this where you use a quotient rule with 1 over cos and then you use the chain rule to square it. But a much easier way is to think that actually we know an identity which connects sec squared and tan squared. So I know that y equals 1 plus tan squared of 3x. And now I can use my known results and my block of 4 really easily. So here y equals 1 plus u squared and u equals tan of 3x, which tells me that dy by du is 2u and du by dx is, be careful of the k, 3 sec squared of 3x. Using the chain rule, which is that dy by dx is the same as dy by du times by du by dx. That means that 2 tan of 3x from 2u times by du by dx, which is 3 sec squared of 3x, which is the same thing as 6 tan of 3x sec squared of 3x. And that's our solution. Okay, good stuff. So when you work through the exercise, you'll have lots of chance to practice doing questions like this. And I hope these examples were helpful. We're just going to look at one more thing today, which is looking at the derivative of the log of mod x. And this is something that is going to come up quite a lot. So the one thing that using the modulus allows us to do is to expand the domain of the natural log. So if I think about what the graph for log x looks like, hopefully we're comfortable with the fact that the y-axis is an asymptote. We cross at 1, and then we have a function that continues to increase, but for whom the gradient gets smaller and smaller. Just be careful when you're drawing log graphs. This does not become horizontal. There is no horizontal asymptote. It keeps increasing, but the gradient diminishes and gets smaller and smaller. This point here is 1. So this is the standard function natural log. But if we apply the modulus here inside the bracket, what that means is if I've got a negative value of x, I make it positive and then I evaluate the log. And what that means is I'm going to get a mirror image, because if I substitute in -1, it's the same as substituting in 1. If I substitute in -3, it's the same as substituting in 3. So this function is going to have a mirror image for negative values, giving us a domain that's bigger than it would otherwise be. And hopefully you're looking at this and you're thinking, okay, I can see it's defined now for all negative real numbers and it's defined for all positive real numbers. However, it is still not defined at 0. So the domain is all the real numbers, but without 0. Okay. We'd have a question then about what is the gradient of a function like this. And one of our standard results is that for positive values, the gradient is 1 over x. And then we just have to think about what happens on the negative side. So to formalize it here, if we let y be our function including the modulus, we're going to consider two cases. The first case we're going to consider is 1 if x is greater than 0. So if x is greater than 0, the function is just log of x, and we know the derivative of that. We know the derivative is 1 over x. But the second case is slightly less comfortable. That's when x is negative. Now, because of this modulus sign, if x is negative, it means the function we're actually looking at is the log of minus x, because x is negative, but what we do is we multiply it by minus 1 to make it positive. And at this point, what we're just going to do is quickly run through the chain rule. So with the chain rule, here what I've got is y equals log of u, where u is minus x. Dy by du is 1 over u, and du by dx is minus 1. So the gradient overall, dy by dx, is 1 over u, which is 1 over minus x, multiplied by minus 1. So, in fact, just 1 over x, the same as before. And this has told us that everywhere the gradient is 1 over x. So, we can write that out clearly, that dy by dx is 1 over x for all x not equal to 0. And if we look back at the graph, this makes sense to us, right? Because the gradient on the left-hand side, where it's negative, is the mirror image of the gradient on the right-hand side, but instead of being positive and everything increasing, it's negative. So the gradient at minus 1, for example, is the negative version of the gradient at 1. So 1 over x. Now, this result allows us to answer any question where we have log of modulus of a function. And this is where it becomes quite powerful, because we can just use the chain rule as we have done before. So what I'd like you to do is one last time just pause the video here, have a look at this question, see if you can figure out how to do it, and thing that I'd like you to focus on is what in particular goes here. X not equal to what values? Pause the video, have a go. Okay, so to answer part B here, the first thing we've got to think about is where is this function defined? And there's two parts to this. We've got the log part, and then we've got the part for the inner function. So the log part tells us that the bit inside the log cannot be equal to 0. And so if I switch quickly and we have a look at the sec x, we remember that sec x does not have any points where it's equal to 0. So that's not a problem in this case. However, we also have to make sure that the function itself is defined. And we look at sec x and we notice that for values where we have an asymptote, the function is not defined. And we think about where that is, and we recall that, well, it happens at odd multiples of pi over 2. It happens at pi over 2, 3 pi over 2, 5 pi over 2. And so this function is not defined when x is an odd multiple of pi over 2. 2k plus 1 over 2 pi. Okay, so that's defined the question. In order to try and solve it and find the gradient, the first thing I'm going to do is I'm going to try and get sec back to something which I can differentiate easily. I'm going to use some of my log rules here. So, I know that sec is 1 over cos. And I know when I take a log of a reciprocal, I can move the power in front. So this is the same as the negative log of cos x. And now this gives me something easy to use. So what I'm going to do here is I'm going to use the chain rule, and I'm going to state it. My outer function is y equals minus log of u, and my inner function is u equals cos x. I'm going to simplify both these things. Sorry, differentiate both these things. So dy by du, the minus sign is retained. So minus 1 over u, and du by dx, remember that cos gives us negative sine x, meaning that overall dy by dx is dy by du times by du by dx, so that's minus 1 over u, which is cos x, multiplied by minus sine x. Minus signs cancel, giving me sine x over cos x, which is, of course, tan x. That's an interesting fact in itself and gives us reason to pause. So the derivative, or the gradient, of the log of sec x is tan x. And I thought we could just look at that quickly before we finish the lesson. So here I've got the graph of sec x, which we've seen before. And what I'm going to add in here now is the graph of the log of sec x. So log of sec x with a modulus is here. This is what it looks like. And what I notice is that the gradient is positive until it becomes infinite, and then it switches to negative until it becomes 0, and it becomes positive and steeper until it becomes infinite, at which point it switches to negative until it becomes 0. And if I put on y equals tan x now, we can see that that describes the shape of the tan x graph. Next lesson we're going to begin by looking at graphs of gradient functions and matching them to regular graphs, and Desmos is a really good tool for doing this. So that's us for the video for today. I just want, if I can get this right, as to just look quickly at the notes and things you've got to do. So we've done a warm-up, we've read through the notes, and then now what you need to do is do practice, and you need to do a very short Google quiz. So those two things are what I'm going to check. This will be the same every time we've done this. What I'd like you to do is I'd like you to complete the Google quiz, and that's very easy, and that will be submitted automatically. Just to give you an idea, there's some questions about some maths, just to check that you've been following what we've been doing, but then also I'm just after some feedback on the videos and whether there's anything you'd like me to change in the future. And then the final thing I want you to do is to submit a photo or photos of your finished and corrected work, and put them via the classroom and this task. So if you're unsure about how to do that, there's a link here to a tutorial to tell you. Please do copy the photos into a Google Doc, because that's the easiest way for me then to provide comments and feedback. Otherwise, that's all for us today, and I hope this was useful. Please let me know, as I said before, all your feedback about it. All the best.